Technology firms and space agencies are exploring space-based data centers to address the rapidly rising energy demand of artificial intelligence workloads. Rising energy demand from artificial intelligence data centers are becoming one of the fastest growing consumers of electricity worldwide, and artificial intelligence is significantly accelerating this trend. Modern AI systems rely on large clusters of graphics processing units (GPUs) and specialized acceleration to train and deploy machine learning models. These systems require continuous high-density computing, leading to enormous power consumption. Unlike traditional data centers that primarily support content delivery and cloud services, AI data centers consume large amounts of energy internally. High-speed data exchange between servers within the same facility or across nearby facilities is essential for training large language models. As the adoption of generative AI expands across sectors, concerns over sustainability, carbon emission, and grid stress are becoming increasingly prominent. Concept of space-based data centers. To address these challenges, researchers are exploring the data of placing data centers in low Earth orbit. The central idea is to power data centers entirely using solar energy available in space, where sunlight is uninterrupted and more intense than on Earth. This approach aims to bypass terrestrial constraints such as land availability, cooling limitations, and dependence on fossil fuel-based electricity grids. Google research project Suncatcher proposes deploying clusters at satellites equipped with computing hardware that can process AI workload in space. These satellites would operate in carefully choreographed orbits that maintain constant exposure to sunlight, ensuring an uninterrupted power supply through solar panels. Technical architecture and design principles. A key feature of orbital data centers is their reliance on dense inter-satellite communication rather than high-speed connections with Earth. AI workload require extremely high internal bandwidth to allow different processors to work in parallel. In space-based systems, this would be achieved through closely spaced satellites communicating with one another using advanced multiplexing and high-frequency disk. Since most data movement occurs within the system itself, the bandwidth required to communicate with the ground station is relatively modest. This mirrors terrestrial AI systems where user queries require limited bandwidth compared to internal data centers during model training. Engineering challenges in space deployment. Despite the conceptual promise, several technical challenges remain. One major concern is exposure to solar and cosmic radiation. Long-term radiation can degrade semiconductor components, affecting performance and reliability. Initial tests conducted by Google indicate that some specialized AI chips can tolerate higher radiation levels than expected, but long-duration missions still pose risks. Thermal management presents another major challenge on Earth. Data centers rely on air or liquid cooling systems. In space where there is no atmosphere, dissipating heat becomes significantly more complex. Data centers in orbit would continuously absorb solar radiation while lacking conventional cooling mechanisms, requiring advanced heat dissipation technologies. Maintenance is also a critical issue. Unlike terrestrial facilities, repairing or replacing faulty hardware in space is expensive and logistically difficult. This raises concerns about system resilience and long-term operational reliability, economic viability, and cost consideration. The economic feasibility of space-based data centers depends heavily on launch cost and hardware durability. Currently, launching equipment into orbit is expensive, but projections suggest that satellite launch cost may decline substantially in the coming decades. Google estimates that cost could fall to around $200 per kilogram by the mid-2030s, potentially improving the commercial viability of orbital data centers. However, space-based solutions must remain competitive with rapidly advancing ground-based technologies. Improvements in renewable energy integration, cooling efficiency, and energy storage can Earth could reduce the relative advantage of orbital systems. Past experiments such as underwater data centers demonstrated technical promise, but were eventually discontinued due to economic constraints. India's interest in space-based data centers. India is also showing interest in this emerging domain. The Indian Space Research Organization is reportedly studying space-based data center technology as part of broader efforts to explore commercial and strategic uses of space infrastructure. Given India's growing AI ecosystem and renewable energy ambitions, space-based computing could become a long-term area of research and collaboration. This aligns with India's broader push towards leveraging space technology for civilian, scientific, and commercial applications, which also addressing sustainability challenges associated with digital expansion.